Phase diagrams and heating and cooling curves. Phase diagrams are not directly on the AP test, so you'll never see a question that has you identify parts of a phase diagram, but you should know the concepts and you can be tested indirectly on phase diagrams. So a phase diagram, it summarizes the conditions of pressure and temperature of which a substance exists as a solid, liquid, or gas. And there will be these equilibrium lines. First of all, solid, liquid, and gas are in the portions there. And these lines right here, these are the equilibrium lines. Right at the line is when those two phases are at equilibrium. So this is the liquid gas equilibrium line. This one's the solid liquid. This one is the solid gas line. And right here, this is the triple point. At that particular pressure and temperature, that is when all three phases will be at equilibrium. So you'll see evidence of solid, liquid, and gas right there at that pressure and that temperature. And this is the phase diagram for water. Water is very unique in that this line right here has a negative slope. Most substances that we come across, it's not a negative slope, it's a positive slope. So the phase diagram will look more like this. Anytime, any phase diagram you have, you can identify that solid will be here, liquid will be here, and gas will be here. Temperature at the bottom, your x-axis, and you will have pressure here at the y-axis. This is another diagram of the same thing. Make sure that when you're looking at those changes of states in matter that you use the word equilibrium in your writing. So when something is melting, going from a solid to a liquid, it is at a state of equilibrium, going from a solid to a liquid. If something is boiling, then it is going from a liquid to a vapor or a liquid to a gas. It is at equilibrium when it is doing that. To determine if something will boil or the normal boiling point, you need to find the atmospheric pressure. And we use the standard atmospheric pressure. So my pressure units on this diagram are in kPa. So I'm going to be looking at this 101.3 pressure line. Where the standard pressure crosses that equilibrium line for the phase changes, that is where you are going to have melting if it is the solid liquid line, or you're going to have boiling. So this is the temperature it boils. And that's called the normal boiling point and the normal melting point. The critical point is a point way off here. It's the point from which no amount of pressure can liquefy the gas. So once I get to this pressure, you will always be at a gas. The higher the critical point, the stronger their intermolecular forces. And we can see with our water here, there's a little gap in our data. The critical pressure and the critical temperature is quite high, showing that water has very strong intermolecular forces. This is just another picture of it if you needed a larger picture to see these phase diagrams. As far as your changing in states of matter, notice they're always associated with those equilibrium lines. So melting is going from a solid to a liquid across that line. Freezing is going the opposite way. Vaporization or boiling is going from a liquid to a gas. Condensing is going from a gas to a liquid. And then the ones down here at the bottom, we're not as familiar with them, but when you go from a solid to a gas, that is called sublimation. And a good example of that is dry ice. If you get some dry ice, it will go directly from a solid to a gas at room temperature. Deposition is when you go directly from a gas to a solid, and this occurs on some cold mornings when you go out to your car that's parked outside and there's a layer of ice on your windshield. So what has happened is the water vapor that's in the air has directly deposited on your windshield, so it's gone from a gas to a solid. Now as you increase the pressure, you will force the substance to go to the most dense state, and this one right here is water. And again, it's very, very unique because of this negative slope line. But if I put it under pressure, so let's say I'm right here. So as I increase the pressure, I can turn from a gas to a solid, but then eventually I'm going to get to a liquid. And that's because for water is the most dense at liquid. The majority of other substances, they look like this phase diagram of carbon dioxide. They are going to have this positive slope here. And so when you put this under pressure, like say if I start here, you're going to go from a gas to a liquid, but eventually you'll end up as a solid. So most substances, the solid is the most dense phase. So let's apply intermolecular forces to these phase diagrams. As the strength of the intermolecular forces increases, what happens to each of the following and why? So again, that would be the forces in between molecules. These are my intermolecular forces. What is going to happen to each of these things? So my boiling point, the temperature is going to go up. So substances that have high intermolecular forces, they will have a high temperature. Viscosity, my viscosity will increase. So it'll get even thicker because those intermolecular forces will stick together more. Surface tension, that will increase. Enthalpy of fusion, so this is the energy required to go from a solid to a liquid, and you will see that this will increase because you are temporarily breaking those intermolecular forces when you're going from a solid to a liquid. Freezing point, that will go up. Vapor pressure, this one will go down. So remember, if you are going from a liquid to a gas, it will make a vapor, and it just does that normally. So if it's water, we call it evaporation. So water just naturally evaporates. Just the molecular motion of the molecules at the surface. Some will get enough energy that they'll be able to escape, and it will form a vapor over that liquid. If you take the vapor pressure, you're going to find that water has a lower vapor pressure than most substances that are the same molecular mass, and that is because it has high intermolecular forces. Your heat of vaporization, this is the heat required to go from a liquid to a gas, and you're going to see that that will be higher because it has an increase in intermolecular forces. Let's look at the relationship between energy and phase change. So again, what is phase change? Melting, boiling, freezing, condensing. These are all your phase changes, and we should add subliming and deposition or depositing. We can actually calculate the energy required to go through each of these steps. This right here is a heating curve. Heating curves are on the AP exam. You might not have all portions of the heating curve on the AP exam, and they might turn it into a cooling curve, which would go the opposite direction. So a cooling curve would look something like this. In your heating curve, we have solid. Then we are melting. If we're going this way, we're melting. Then we are at a liquid phase. Then we are boiling, if we're going this way. And then we have our vapor. At boiling and melting, notice that it says equilibrium. These are the phase changes. And remember, at phase changes, you're crossing that line, that equilibrium line, and so you should have both phases there at equilibrium. In other words, both of them are present. If we're cooling something down, we're just going the opposite. So we have our gas, we have our condensing, we then have our liquid, and then we have our not melting, but freezing, because we're going the other way. And then we're going to have our solid. But we can calculate the energy required to heat it. So if I'm going this way, I'm putting energy in. So this is endothermic because energy is going in. And if I'm taking energy out, this would be my cooling curve. On this one, this would be exothermic because I'm removing it. So again, in orange, this is the cooling curve. The formula to figure out how much energy is required to go through these different states of matter. And in this example, we're going to be using water the whole time, but you really could use any other substance. Is this formula. You're going to use this formula. Q equals mc delta T. So Q is the quantity of energy. It's also called the enthalpy, and it is measured in joules. That C is the specific heat constant. And the delta T, that is a change in temperature. So for delta T, you always do the final temperature minus the initial temperature. During a phase change, melting or boiling, the temperature does not change. And we'll look at that cooling curve again so you can see that. And so because of this, the formula is just a little bit different. So I really just take that delta T and drop it. So you can just cross that out. During phase changes, they don't use that specific heat constant. Instead, they use the enthalpy of fusion or the enthalpy of vaporization. So, but it really is just a constant, and they have to give you the constant. So the delta H and the C, they have to give that to you. you're not required to memorize it. These are all the constants that you're going to use when you use a heating curve in this example, and each of the areas corresponds to a part of the graph. So if you're at a solid, you're going to use that constant. So if you're at the solid portion, if you are melting it, then you're going to use that heat of fusion. And then if you are heating water, then you're going to use the specific heat of water. And if you're boiling, then you'll use that heat of vaporization constant. And then if you are in the gaseous phase, then you'll use that specific heat of steam. So as I mentioned before, it's endothermic when you are heating it, and it will be exothermic when you are cooling it. And just a note on our heat of fusions, so melting is 334 joules per gram if we're working with water, but to boil it is 2,260 joules per gram. How come the heat of vaporization is so high? And that's because you are completely breaking the hydrogen bonding. Just melting it breaks it a little bit, but it reforms. So you do have to put some energy in to break the crystal lattice structure of ice. But to go from a liquid to a gas, you're completely breaking that hydrogen bonding. And so it does require a lot of energy to do that. So we're going to do this problem. All of our constants are given to us. And the first thing we're going to do is we're going to see where we are on this heating curve. So it says how much heat is needed to change 100 grams of ice at 10 degrees Celsius. So on the graph, I know that I'm starting at minus 10. So this is when it's ice. And then it says we're going to end up at 110. So that's over here. This is steam, and I'm at 110 degrees Celsius. So I'm going to go through all 5 areas of this heating curve. So there are 5 steps to this problem. If we were just stopping at 50 degrees Celsius, that would be only 3 steps. So each portion of that heating curve has a different equation. And then I'm going to add up all 5 steps, all 5 equations to get my final answer. All right, let's start off with area A. So area A, this is where I'm at ice. I'm going to write my formula, Q equals mc delta T. And then I'm going to put in what I know. So I know that the mass of my ice is 100 grams. And then I'm at area A, and so my specific heat for ice is going to be 2.06. And I'm just going to jot down my units so that I can see that they will cancel. And then my change in temperature, so my delta T is again final minus initial, so I have 0 minus a negative 10. And so that is going to be a positive 10. Let's cancel out our units. And so I am left with joules, and doing the math, I get 2060 joules. So that's just to get my ice up to the point where it's going to melt. The next portion of the curve, I'm going to melt the ice. So I use the same equation, except for I'm going to get rid of the change in temperature. So it's just the mass times the constant. So again, I still have my 100 grams, and I'm going to this time use that heat of fusion constant. Notice that the heat of fusion just have joules and grams because, again, the temperature doesn't change during the phase changes. The reason the temperature doesn't change is because the energy is going to breaking the bonds, the intermolecular forces, instead of just making the molecules move faster. So doing my math, I get 33400, and that is in joules. All right, now that we've melted that ice, so it's at the liquid state, so I'm at 0 degrees Celsius as a liquid. Go back to my formula. My mass is still 100 grams. My constant is different. This is the specific heat. When I look at my temperature, my final temperature is 100 degrees Celsius because at that point it's going to boil. So I'm just in the water phase. I'm going from 100 minus 0. So I get 100 degrees Celsius. So on this one, we're moving through a lot of temperature. So my number is going to be a little bit bigger because of that. So I get 41800 joules. That's for area C, or the liquid area. Let's go to D. So now I'm boiling. And again, Q equals mc delta T. But the temperature's not there. You can cross that out. So I just have my mass. And this is multiplied by my heat of vaporization. Again, just joules per gram. Grams cancels out, and I am left with... So notice this is where most of my energy goes to, is to boil it. Because again, you're completely breaking those intermolecular forces. And then my last step, now that I'm in the vapor phase or that gaseous phase, so I'm just at steam. So Q equals mc delta T. And put in all my numbers, so 100. And then my delta T, again, final minus initial. So my final is 110 and my initial was 100 because that's the only area where it's going to be steam. So I'm going to have 10 degrees and I get 20 joules. All right, so for the final answer, you're going to add them all up. So again, add them up, all of them. So in this case, I have 5 steps. And when I add them up, I get 305, 280. Obviously, I'm not looking at sig figs. I'm going to divide by 1,000. And so when I do that, I get 305 kilojoules. So anytime you're doing energy, make sure you put your unit. So if I were to put that 305,000 joules, I would get credit for this. And I would also get credit if I change it to kilojoules. So there it is. So 305 kilojoules to go from 100 grams of ice all the way to 100 grams of steam. So this is not one calculation, it's 5 because 5 different things are happening. In area A, my solid particles are just moving faster as I add heat. In area B, I'm melting it, I'm breaking that hydrogen bonding. It breaks and reforms, and so it's not completely broken. In area C, I'm making the molecules move faster, so they have more kinetic energy, but it's still a liquid. In area D, I am turning it into steam. The energy is going into completely breaking that hydrogen bonding of my water. And then in steam, the energy is going into making the molecules move faster. So my gas particles just move faster. Let's do some more problems just to practice. So look at the first one. How much energy in joules does it take to melt 200 grams of ice? So on my heating and cooling curve, I am only right here in the melting portion. So that's area B, the second area. So Q equals mc delta T. But remember, my temperature doesn't change in a phase. So I get rid of the delta T. And my mass is 20 grams. And my specific heat constant for melting is 334. And let's do our math. My final answer is 66,800, and that is joules. So that's how much energy to melt 200 grams of ice, and I'm only in that melting portion. The second one, how much energy in joules is released when 50 grams of water condenses? So I'm just going to draw my heating curve, but I am right here. I'm just going this way. I'm going backwards. So write my formula. This is a phase change, so I can get rid of that. So my mass, 50 grams, and then I look up the enthalpy. It should be given to you, and I just do my math. So on this one, this is how much energy will be released. And so a lot of times they'll put a little negative sign showing that it is leaving the water. So you can't have negative energy. The negative sign just shows the direction. So because I am cooling this, this is how much energy will have to leave in order to condense steam into a liquid. Let's look at this. How much energy does it take to heat ice from minus 20 to 20? So on my heating cooling curve, I am going to be in these 3 areas right here. So this is a 3-step problem. So first of all, Q equals mc delta T. I'm just heating my ice. I didn't do a mass, so let's just do 20 grams. That has to be given to you. I didn't write the question right. Okay, 20 grams, And then my specific heat of ice, my temperature. So I'm going from 0 minus a minus 20, so 20 degrees Celsius. And I get 824 joules for that step. Now I'm going to melt it. So again, your formula changes a little bit. And I'll write it as a delta H this time. They would accept either way. Grams, and then this one is going to be 334 joules per gram, 6680 joules for that one. And then next I'm going to just heat my water. I use a specific heat of water. It's a little bit higher. A lot of substances have quite lower specific heats, but liquid water has a very high specific heat. It can absorb a lot of energy. That's why we use it as cooling in our cars and cooling in our nuclear power plants. Again, 20 degrees Celsius minus 0 gives me 20 for that change in temperature. And I get this answer. So my final answer, I have to add up the 3 answers I got. And I get as my final answer, if I did my math right, 9,176 joules to take this from ice to 20 degrees Celsius water. As far as sig figs, if there's 2 of them, I did a poor job again writing this question. I would say 90 to 100 joules. On these heating and cooling curves, the slope of the line lets you know how high the specific heat capacity is, and it's an inverse relationship. So if I have a really, really steep line like this, that's usually some sort of metal because they have a low specific heat. And you can see over here, water has a very high specific heat, so the slope is a little bit more mild. So the water slope is not as steep as, say, a metal would be.